Welcome to Concrete Technology. Today we are going to discuss about cement, its composition and manufacturing process. Before you're being introduced to concrete technology, I'm sure that you have come across the term concrete. Okay, first let's discuss what concrete is and how it's being made. Concrete is a mixture of cement, fine aggregate, coarse aggregate and water. What I am saying is for a normal concrete. For engineered concrete, it may require an addition of admixtures. Okay, this is what about concrete. Concrete is made up of aggregates embedded in cement, sand, mortar, and also this concrete can be called as a composite since it involves different materials like fine aggregate. Fine aggregate is nothing but sand, coarse aggregate, water, etc. Next, going into the topic, before going into the topic, we would just see how this concrete came into existence, from when we started using the concrete and why it's of much importance since we are building many engineered structures using the material concrete. Right from Indus Valley civilization to Statue of Unity, we have involved many building techniques for building a structure, and this proves to be an identity towards development. Likewise, concrete too has its own evolution period and development period. The evolution period started right back from 3000 BC, that is during the Egyptian period. That is the period when they built pyramids. For building pyramids, what they used was they mixed mud with straw and they formed bricks, and for the brick binding they used mortars. And next evolution came in Roman and Greek period, that is around 600 to 300 BC. That is, they built structures which is remarkably same to that of structures which is being built today, namely Pantheon and Colosseum. And again the technology took a leap forward in 17th century, in the middle of 17th century, when John Smeaton introduced a term hydraulic lime when he used for a renovation work in an Eddy lighthouse in England. And after that it took a great leap forward, and from there many works came into existence and many technology development took place for this concrete. In 1824, Joseph Aspdin, known as father of Portland cement, founded that while burning clay and lime minerals, a hard material came into existence when mixed with water, and it resembled a rock in Portland. So he termed that cement as a Portland cement, and he got patented for it, for the cement. And this is how the history of concrete has come through. Next, now we are going to see about the cement, its composition and how it's being manufactured and the types of cement. Okay, well, before going into the manufacturing process, let's have a look about the approximate oxide composition limits of OPC. That is, OPC is nothing but ordinary Portland cement. The approximate oxide composition of ordinary Portland cement consists of CaO, it can be termed as C, SiO2S, Al2O3 as A, Fe2O3 as F, MgO, alkalis and SO3. CaO, the percent content is around 60 to 67 percentage. SiO2 17 to 25 percentage. Al2O3 is 3 to 8 and Fe2O3 0.5 to 6. MgO, magnesium oxide 0.1 to 4, and alkalis will lie around somewhere between 0.4 to 1.3, and sulfates SO3 around 1.3 to 3 percentage. This is the oxide composition of an ordinary Portland cement. As we discussed already, concrete is nothing but it is made up of an aggregate embedded in cement and mortar, and this aggregate forms a skeleton matrix which constitute about 60 to 75 percentage of volume, and remaining 25 to 40 percentage is occupied by cement paste, and other 1 to 2 percentages of voids in the concrete. And as we said already, it is a composite material, that is the aggregates are being embedded in a cement paste mortar. Again, that in the cement paste mortar, the sand is being embedded in cement paste, and again if we go in deeper into the cement paste, there are many zones known as gel pore, capillary pore, interpose, water, etc. So it's just an agglomeration of many particulate matter. Also we can call concrete as a particulate matter. Next we are going to see about the advantages and disadvantages of concrete. Since it's being used next to water, let's see about its advantages and disadvantages. Advantages: lower life cycle cost. Concrete is relatively a cheap material since it's being involved in many construction process. The initial capital cost and the maintenance cost during its service period is relatively cheap compared to other materials. Next, moldability, that is we can mold it into any desired form which we like to have. Robustness is nothing but the massiveness which it gives. Robustness is nothing but the massiveness which it gives to the structure and which we can't expect from other materials, since the cost involved will be more when we expect that in a steel and other materials. And next is it can be designed for desired property. Since it is a particulate matter, we are combining two and more materials of different nature, but even though we can design it for the desired property, that is what property we expect the concrete to do, that we can design in that way we can design the concrete, even though when we are mixing a heterogeneous materials. This is all about the advantages. Next, about disadvantages. Since advantages compared to advantages, disadvantages is limited to just only few points. Low tensile strength. As we already know, concrete is strong in compression and weak in tension. That paves the way for disadvantage, that it doesn't have tensile property to withstand the tensile stresses. Next, low ductility, that is a ductility, it can deform into any shape, it can deform to a extent before attaining failure, that is termed as ductility. But concrete is poor in ductility performance, and that paves the way for its disadvantages. Next, we go for the raw materials for concrete production. These are the main raw materials used for the manufacture of cement. This calcium carbonate is abundantly found in limestone, and the silica, alumina and iron oxide are available in clay minerals. and these two when combined with water will give a hardened paste called as concrete. Now we have seen the raw material for cement manufacturing process. Now we are going to discuss about the manufacturing process. This manufacturing process has been divided into two groups, namely dry process and second one is wet process. In modern periods, that is nowadays, we are using this dry process. This wet process, once it has been in existence, and now no one is using this wet process since it consumes more energy. Anyway, I'll discuss about both dry and wet process. First, let me discuss about the dry process. In dry process, the basic raw materials which I told you, the clay and the silica, clay and the other minerals are being excavated from the quarrying of limestone and clay. Next, second process is grinding. The quarried materials are grinded to fine size, and after the grinding process they are being passed into the hoppers. The first step involves quarrying of limestone and clay, and second, the quarried materials are being grinded to fine sizes, and the third step involves the passing of those grinded materials through hoppers which are already preheated. The next step involves after passing through this hoppers, they will enter the entry into rotary kiln. After the materials are being passed through preheated hoppers, they are being entered into rotary kiln. In the rotary kiln, the temperature will be around 1500 degrees Celsius, where the material sinters, that is without melting the materials, by just heating we are combining two materials, that is here the main materials being limestone and clay. For a cement manufacturing process, we are in the process of combining the two, and that is being achieved in this rotary kiln by where the temperature is around 1500 degrees Celsius. The material sinters, that is they combined when exposed to a higher temperature. And after the rotary kiln, at the end the clinker is cooled and grinded with gypsum. Here, after the entry into the rotary kiln, that at the end of the rotary kiln, these materials will come in the form of clinkers, that is a small sized ball sized particles. They are called as clinkers, and after cooling the clinkers, they are again grinded with gypsum and they are stored in silos and packed. Now let's discuss about the wet process. Wet process includes the same as that of the dry process, but after quarrying of a limestone and clay, what we are doing is, during grinding we are mixing it with water, 40% of the water, and after mixing with water we are again burning it, and after burning again they are being passed through rotary kiln, and from rotary kiln the final end product clinker is obtained, and again we are from that clinker we are breaking the clinker and grinding with the gypsum before leaving for selling. The main disadvantage with this wet process is consumes more energy. So nowadays we are just using the dry process alone to manufacture a cement, and this is how a cement manufacturing takes place. And I have explained the dry process method of cement manufacturing through a schematic sketch which I will show you now. And this is how a cement manufacturing is done. Now we are going to see about the chemical composition. This is the oxide and this is the percent content. Already we have discussed calcium oxide 60 to 67 percentage, silica oxide 17 to 25 percentage, aluminum trioxide 3 to 8, ferric oxide 0.5 to 6, magnesium oxide 0.1 to 4, alkalis 0.4 to 1.3, is sulfates 1.3 to 3 percentage. This is the approximate oxide content required for a cement manufacturing process. And now we are going to see how these oxides are being combined to form the end product cement. And during the manufacturing process, the individual oxide elements are combined to form a compound element, and the compound element plays a major role when it's being used in structures. Now let's see how these oxides combine to form compound elements. C3S, C2S, C3A, C4AF. This is the final end compounds when these oxides are being combined in the rotary kiln, and these four compounds are collectively called as Box compound. The mineral name of this C3S, that is tricalcium silicate, is alite, C2S belite, C3A aluminate, and C4AF ferrite. Box compounds are C3S, C2S, C3A and C4AF, and this alite, belite, aluminate and ferrite are the mineral names of these individual compounds. And now in this diagram I will explain you how these compounds are being formed at different stages. Now first, that is a rotary kiln where the temperature is around 1500 degrees Celsius. The kiln is somewhat inclined in nature. First, around 450 to 800 degrees Celsius, the zone is called as dehydration zone, where the water gets evaporated. If any water is being there in the oxide form, it gets evaporated. Next, after 800 to 1200 degrees Celsius, that is called as calcination zone, that is the limestone decomposes, and that's the stage where the initial formation of compounds take place. And around 1200 degrees Celsius to 1350 degrees Celsius, the initial formation of C2S gets started, that is the belite component will be formed first, and after that C4AF will be formed, and after that first belite will be formed around 1200 to 1350 degrees Celsius. After that C4AF will be formed, and after that C3A, and at last at the end of the kiln C3S alite will be formed, and after that it gets into the cooling grade, that is where the clinkers will be cooled, and finally we will grind the clinkers with gypsum and we will send for packing. This is how the oxide elements are being combined to form compound elements. Next, see about the control ratio, that is how these compounds should be, within which limits these compounds should be there, that is termed as control ratio. First is these three factors governs the box compound, that is based on these three factors the proportion of C3S, C2S, C3A and C4AF is being governed in a cement. Let's see what's this lime saturation factor. Lime saturation factor C divided by 2.8 S plus 1.2A plus 0.65 F into 100%. It's being expressed in terms of percent. S divided by S plus F. And next, alumina ratio A by F. This lime saturation factor is expressed as a percentage of calcium oxide to silica, alumina and iron. And what they are telling is this lime saturation factor should not be greater than 100%. It should be somewhere around 95 to 98%. The reason why it should not be greater than this is it leads to free lime, that is with the lime, if the lime, any free lime is there, then it causes a trouble during the hydration process, and that's the reason why they are using this lime saturation factor as a control ratio. Next, silica ratio, that is the ratio of silica to silica, summation of silica and iron. And next, alumina ratio means it's a factor of alumina to iron. Higher silica ratio means more C3S and less C3A. In a cement, if this silica ratio is high, then it indicates that only the allyde component is more compared to the aluminate compound. It should not be like that. And also higher alumina ratio means higher C3A. That is, when alumina ratio is high, we will be getting higher C3A. When silica ratio is high, we will be getting more C3S. In a cement, these each and individual compound should be within the prescribed limits, and why it should be within the prescribed limits we will be discussing later during the hydration process. And now we are going to discuss about the compound composition, that is how these elements, these compound should be when they are being combined into a compound. I am just writing the percentage alone. C3S 54.1%, C2S 16.6%, C3A 10.8%, C4AF 9.1%. And this is the compound composition for an ordinary Portland cement. That is, when we are making an ordinary Portland cement, we should get the compound composition in these prescribed ranges. Then only they belong to a category called OPC, and these compound composition is being governed by the already set factors like alumina ratio, silica ratio, lime saturation factor, etc. Now just I'll show you a flow chart of how cement is being manufactured right from the basic mineral ore. First is raw material for cement, that is, as I said already, limestone, clay or shale is being quarried. Then in that the compound elements are available in the compound elements in raw materials are of in the nature free oxygen, silica, calcium, alumina and iron. And in oxide composition, that is when we are quarrying the mineral, we will be getting it in the form of calcium oxide, silica, alumina and iron, ferric oxide. In compound composition, that is after these compounds are being combined in a rotary kiln, we will be getting the compounds called as C3S, C2S, C3A and C4AF, and that based on the compound composition we will be getting various types of cement called different Portland cement. And when these Portland cement is being hydrated, that is when they are being combined with water, the final end product will be CSH gel plus calcium hydroxide. The formation of CSH gel and calcium hydroxide will be discussed later. Now we are going to see about the different types of cement and how this different types of cement is being arrived. This different types of cement is being arrived by varying the composition of this compounds. That is, if C3S, C2S, C3A, C4AF composition is being varied, we will be getting different types of cement. Now let's see about the different types of cement. Types of cement: ordinary Portland cement, and in the ordinary Portland cement we have around 3 different types, that is based on grade they are differentiating 33, 43 and 53 grade. Next is extra rapid hardening cement, sulfate resisting cement, quick setting cement, oil well cement, hydrophobic cement, and likewise we are having different types of cement, and these different types of cement have a specific Indian specification number, Indian standard specification number. That is, if this is to be a product belonging to OPC, then it should have a certain features, and that is being governed by IS codes. For each cement we are having different IS specification number. Based on that we will be able to classify the different types of cement, and these different types of cement are meant for different purposes. Suppose when we are using rapid hardening cement, then our strength attainment will be higher when compared to that of a ordinary Portland cement. In extra rapid hardening cement, compared to rapid hardening cement, we will be attaining the strength attainment earlier. That is, based on our purpose we are deciding how the cement should work, and based on that we are having around this much type of cements. Likewise, we are having super sulfate cement, sulfate resisting cement, low heat cement, hydrophobic cement, alumina cement, air entraining cement, colored cement, etc. And each one has its own feature depending upon its applications. And for that purpose we have slightly modified the composition, what I told you already. That is, by varying the compound composition we will be able to achieve the different types of cement.